This is the screencast for section 8.2, example 9, working with the indeterminate form 0 to the 0. Again, you've got this exponential situation, so that clues me in that I'm going to be using logs, but let's see what the actual problem looks like. Determine whether the limit as x approaches 0 from the right of x to the x exists, and find its value if it does. So first we need to determine that it exists. Well, that's going to be from the graph. So what I said was graphical analysis shows that the limit as x approaches 0 from the right of x to the x exists. See, it should approach, it looks like about 1, but the limit as x approaches 0 from the right of x to the x is in fact 0 to the 0. So that's the indeterminate form we're working with, which tells me I'm going to start out by taking the limit as x approaches 0 from the right of the natural log of f of x, which is the limit as x approaches 0 from the right of the natural log of our function x to the x. Alright, so now let's see if I can simplify a little bit. I brought the x down as a coefficient, which again we want a 0 over 0 situation, so I put the natural log in the top and then divided by the reciprocal of x instead, which does give us a, not 0 over 0 actually, but this time infinity over infinity. As x approaches 0 from the right of the natural log of x, as we're coming in from the natural log curve, we go down to negative infinity, then 1 over x, as 1 is getting divided by smaller and smaller and smaller positive numbers, that will approach positive infinity. So the indeterminate form this time that we're working with is still a quotient, so we get to use L'Hopital's rule, but this time it's negative infinity over infinity. That's fine. So now I'm going to take the derivative of the numerator, which is 1 over x, the derivative of the denominator, which is negative 1 over x squared, simplify, plug in 0, and I get 0. That's not my answer. That was the limit as x approaches 0 from the right of the natural log of our function. So we can now make the conclusion that the limit as x approaches 0 from the right of f of x, which can be written as the limit as x approaches 0 from the right of e to the log base e of f of x, so natural log, which I found the value for the exponent, that was 0. So the answer is e to the 0, which is 1. So now try problem number 23, says identify the indeterminate form and evaluate the limit using L'Hopital's rule. So the limit as x approaches 1 of that trinomial to the x minus 1. Well, if I plug in 1, I can see that I'm going to get 0 for an exponent, and then my base is in fact 0. So I have 0 to the 0. Again, an exponential situation using logs is going to help me out. So the limit as x approaches 1 of now the natural log of our function will equal the limit as x approaches 1 of the natural log of the actual function. So I'm going to drop the x minus 1 down as the coefficient, but remember we don't want it to be a multiplication situation, we want it to be a division situation, so we can use L'Hopital's. So I'm going to just right off the bat write in the denominator 1 over x minus 1, the reciprocal of what that coefficient would have been. If I plug in 1, this trinomial is going to approach 0. So the natural log of 0 doesn't exist, but as we're approaching 0, we're going to get negative infinity. And then 1 over x minus 1, well, that's going to be 1 over 0 as x approaches 1, the denominator is approaching 0, so that's also infinity. So we'd get negative infinity over infinity. So I can use L'Hopital's rule here. I take the derivative of the numerator, 1 over x squared minus 2x plus 1, times 2x minus 2. Don't forget the chain rule. All over, now that's going to be negative x minus 1 to the negative 2. Simplify, simplify some more, simplify some more, and that's a lot easier to work with. I have these messy fractions, so I put the 2x minus 1 in the numerator, factored out the 2 so I could cancel out the x minus 1s. In the denominator here, this had an exponent of negative 2, so I made it a fraction, and then I multiplied by the reciprocal, simplified, you get the idea. Now I can plug in 1, and I see that the limit as x approaches 1 of the natural log of our function is going to be 0. Therefore, the limit as x approaches 1 of our function, which can be written as the limit as x approaches 1 of e to the natural log of our function, is going to be the limit as x approaches 1 of e to the now 0. So e to the 0 is 1, and that is the limit that we were trying to find.